Swayam Prabha. Digital India. Educated India.
Right. So, um, so the critical components of an experimental setup of 2D is, of course, your source of short pulses, typically a NOPA, which is then output of a NOPA, which is compressed. Then we have to divide our pulses into uh, 4 pulses, forming the vertex of a boxcar geometry. The way to do that, again, not going to discuss how we do that. We use a diffractive optical element, bit of diffractive optics, uh, which basically splits the beam into 4, which are emitted along vertices of a square, which can be then collimated, and you have these 4 beams coming in there, which have to be focused on the sample, right? And then the emitted signal should be heterodyned with a local oscillator and measured. You measure the spectrum, and you have to scan the delay between the pulses, both the delay between the first and second pulse, which explores the coherence dynamics, and sometimes you also want to change the delay between the second and the third. You want to be able to generate 2D spectra at different population weighting times, right? We have seen that, for example, in the context of spectral diffusion, so on and so forth. So let's kind of unravel each one of that. So first I want to go and talk about how do you focus these beams reliably on the sample. Seems pretty simple task. You will say, put a lens, which is already there. It's a lens. It's going to take care of things. It's easier said than done. So I want to focus on that part, on the focusing of the pulses. I'll show you why this is important. The second thing I want to talk about is what are the various methods with which you delay one pulse with respect to the other. I'm going to highlight one particular method which we implemented. Okay, the first part, how do you overlap femtosecond pulses keeping the phase matching intact? That is extremely critical. The K vector phase matching is very important, right? So you know, for refacing or non-refacing, you have minus K1 plus K2 plus K3, or K1 minus K2 plus K3, so on and so forth. And this phase matching is very, very important. Now you can define for a beam a particular phase front, right? So this is your diffractive optical element. Let's say it's generating your beam, and you have this phase front associated with each of this beam. And you want this phase front, if you see my hand, you will see, you want this phase front to kind of converge onto the sample reliably. If you come with a phase front, something like that, what happens is that you'll have some kind of cross coupling like this, and that will completely disorient the phase matching. You'll start generating artifacts because now you are in this configuration. You will have phase matching conditions beyond what you want to be. Okay, that's a very important thing. So how do you ensure the phase fronts? But you have a collimated beam coming like this, you're focusing. The phase front should not be doing this. Let me explain it a bit more and why this is important. So the way for doing this, let's take a step back and recall, if you have already done, if not, know some details about scalar diffraction theory. Scalar diffraction theory says, if I have a beam of light, even though it may be collimated, perfectly collimated, as I let it propagate in space, what happens? A Gaussian beam will undergo transformation, will expand. Okay, and that expansion, based on scalar diffraction theory, can be written as this form, where my spatial distribution as a function of x, y, z is related to my spatial distribution at x prime, y prime, for example, using this expression. Okay, I'm not going to derive this. This can be derived using, this is coming from Fraunhofer diffraction theory. I'm going to derive this. That is one part. So even if I take a collimated beam, it will have some kind of divergence and a specific kind of propagation. Secondly, we are using a lens to focus. When you use a lens to focus, I come with parallel wavefronts from a collimated beam. They will generate spherical wavefronts like this. So in the sense, I'm adding a phase to my input form. So this is my input distribution, phase wavefront, and I'm adding a particular phase, a spatial phase, if I may call it, to this, and which can be written of this form, sort of a Gaussian. Right? So if I just take my beam, collimated beam, don't think of 4 pulses, just 1 pulse, right? Collimated beam, send it through a lens, you will see it will have now an optical phase, sorry, a spatial phase, which will open up additional k vectors where you don't want it to be. You agree with me on that? Right? For getting the perfect condition, you want to have perfect thing. You don't want a distribution of this, right? And that's something that your lens effectively does. Is there a way to overcome this? Is there a way to circumvent this problem? The answer is yes, and that answer lies in Fourier optics. Let's talk about that. Let's take a condition where I have an input field distribution at a length, focal length from the lens, and I'm looking at the output field distribution exactly at a focal length from the lens. Okay. In this case, using scalar diffraction theory and also the phase modification induced by the lens, I can write it like this, where this part is the phase added by the lens, and this is just a propagation part. Okay, I can give you these notes and you can kind of verify this. A very good text in this context is Introduction to Fourier Optics by Goodman. It's kind of an excellent text if you want to go over this. Now I can take this part, I can solve this. Okay, I can kind of simplify this and I get an expression of this kind. Okay, now I'm going to ask a tricky question, but maybe some of you might know. Does this expression, this complicated looking expression, remind you of something? Does it remind you of something? I'll give you a hint. Make a transformation like this. Let's define 2 parameters, fx and fy, like that. Does it remind you something? Fourier transform, excellent. And that's great that you were able to see this. Non-trivial, very good. So in fact, you can show that exactly at the back focal plane of the lens, I have the Fourier transform of the whatever field I have at the front focal plane of the lens. A lens is doing a Fourier transform. Okay, this you can do in the lab. You put a pattern of some kind, you get a beautiful Fourier patterns, and then you can manipulate it. In fact, this is one of the few very first experiments I did as, I don't remember, as an undergrad or master's student. Professor Shiva was there guiding me through this experiment. But this was one which fascinated me like anything. It's really exciting that you can manipulate the spectral content, the spatial distributions of your spatial distributions by accessing the Fourier space physically. Very powerful. Okay, now let's say I go to a situation where I repeat this with another lens. What I have now is, with this lens, I will do an inverse Fourier transform of what? Of this one, of this field that I have Fourier transform from here. This pattern, whatever you call it, the distribution. So basically my U out exactly at the back focal plane of my second lens will be exactly the same as the distribution, the phase pattern on the front focal plane of my first lens. Okay, you have relayed the information both amplitude and phase wise from the front focal plane to the back focal plane of this system. This is called 4F relay imaging, which is used for many things, including for polariton dispersion, for example. So it's kind of very powerful, very powerful. And in fact, this has to be done. So if I'm getting the spatial pattern from the DOE, whatever pattern my DOE is refractive optical element is generating with my 4 beams on the 4 vertex, I need to relay image that pattern on the diffractive optical element onto the sample. So you cannot simply place a lens, you need to do a relay imaging. Okay, that's a very important thing. In fact, relay imaging is probably the best way to overlap femtosecond pulses artifact free, if you can do it properly. It's a very powerful tool. Okay, that's the first part. So you need to somehow relay image the pattern on diffractive optical element which generates this onto the sample. That's first part. Let's talk about the second part. I want to now apply delay between the pulses. Delay between the 2 pulses, let's say between A and C, or C and A, or sometimes C and B. How do you actually in the lab delay 2 femtosecond pulses? What do you do in the lab, anybody? Delay line, right? So you can put one on a delay line and do it. So there are 2 delays that we have to complete to kind of control. So we need 2 delay lines to kind of do this, right? But then to do that, I said so much about relay imaging and so on and so forth. You need to now take out the output from the diffractive optical element which generates the pattern, then put it on some delay stages, get them back onto onto the same path, then relay image onto the sample. Kind of complicated, not impossible. People do it, everybody can do it. It's complicated. Secondly, moving parts. Moving parts intrinsically create instabilities because they move, and then they're on pose, there are additional pose, and so on and so forth. It creates instability. And interferometric measurements, these add noise. Okay. Third important thing. So if I take this delay, this is oscillating at the frequency of energy difference between 2 states. Let's say these 2 states are separated by 1 electron volt or even 2 electron volts sometimes. That's the range. So what should be the kind of temporal step that you need to do to kind of get that oscillation? Extremely short. Sometimes you may not even have the resolution. It's kind of very unstable, right? So there are 3 problems if I physically simply delay the 2 pulses. Agreed? It's not impossible. You can do it, but I don't recommend you do it because it's not easy. So instead, there is a very neat way. This was proposed by Keith Nelson at MIT. This is called Colbert. It's called Colbert because of its coherent mixing. I don't remember that. It's an acronym for something. I don't remember the actual thing. The joke is that it should not be put on Zoom. The recording was kind of a joke. I can tell you the joke. So I met the guy who kind of worked on it while at Keith Nelson's group. Keith Nelson's group, there was Daniel Turner, Catherine Stone, and Kenan Gundogdu, all 3 now extremely successful professors. They were all working with Keith Nelson at MIT, building this Colbert, and they wanted to become famous. And that time, Stephen Colbert, who was a kind of a comedian, was getting famous in the US. So they somehow made an acronym which spelled like Colbert, which is Colbert, to be on TV, but they were not on TV at the end. But that was a kind of a joke. Anyway, the way to do that is using pulse shaping method. Of course, pulse shaping was done much before this, but pulse shaping utilized for 2D spectroscopy was done by Keith Nelson. So in pulse shaping, it's not that different from 4F imaging. So now come with a pulse, right? Come with a pulse. Remember, our pulse has broad bandwidth. It has broad bandwidth. So put a diffraction grating. What does a diffraction grating do? Disperse it in wavelength, right? I disperse it in wavelength. So it dispersed right here in wavelength. It's going in this direction. And I do Fourier imaging. Okay. What is getting dispersed? Something in frequency, right? And that is getting Fourier transformed. So what are you accessing here? Fourier transform of frequency field, in a sense. You're accessing the temporal components in a sense, right? So it's kind of very beautiful way. So what we do is in the 4F system, so you come with a field, you disperse it exactly at the Fourier plane, which is basically the back focal plane of the first lens. You introduce a spatial light modulator, which is a liquid crystal display, which is there. There's no projector anymore here. There was a projector. Liquid crystal display is SLM is what is used in a projector to project patterns. Basically, you can apply a phase or an amplitude mask. Okay, basically you apply a voltage, and depending on the voltage, the liquid crystal molecules will align, and that will enable you to, of course, pixelated, and then you apply phase and amplitude mask pixelated as a function of some x spatial direction. Okay, remember now I have, if I apply some kind of phase mask here as a function of x, that is equivalent to applying a phase mask as a function of frequency, because I have dispersed the frequency. Okay, in fact, I can write my expression exactly of my phase applied by SLM. This is my amplitude and some phase term here. And then if you look at the electric field at the output, you will get a sinc function of this kind. By the way, this is after the second Fourier transform. So you apply the phase mask, and then you have this particular lens doing an inverse Fourier transform, and then you will generate again my electric field as a function of frequency, and it will have now this form where you have added effectively a phase function to your input electric field. Okay, that phase enables you to shape the pulse the way you want. Inherently, you will also get this sinc function. The sinc function is simply coming from diffraction from the pixels. On the SLM, it's inevitable. You kind of will never get a clean pulse. You will always get some sinc oscillations at the end spectrally, but that's fine. It doesn't really affect us so much. In fact, this method can be used to compress the pulses. So remember, when I have broad bandwidth, I will have some kind of phase which is not flat over the entire spectrum. I'll have some phase distribution, and compressing the pulse is equivalent to making the whole phase flat over the entire spectrum. So you can apply patterns on the SLM in order to compress pulse, which is what we do. This is called MIPS algorithm, again developed by forgetting the name of the group. I'll tell you. Oh my god, I'm forgetting the name. Anyway, so it's another way of generating or compressing the pulse, which is what is actually shown here in the thing. Now let's take a condition where you apply a linear tilt in space profile. A linear tilt. Okay, phi of x on the SLM is minus some k times x. Now that will correspond to a linear spectral shift of minus 2 pi nu times tau. Okay, the tau depends on how much is the slope of the phase that you apply, the linear phase. Now if I write it in terms of my electric field, then this is my phase here. That is my phase that I apply, e power I 2 pi nu tau is the phase that I apply to the electric field profile. And if I convert it to time, what I get out is actually a field which has been delayed by certain time tau, right? So what you do is that you have certain field distribution to begin with. The first lens and the grating will convert E in of t to the Fourier transform. The SLM will add my phase, and the second lens will do the inverse Fourier transform, will get out my E of t. So the second lens reconstruct the time domain shape pulse via Fourier transforming this. Okay, that's the kind of detailed method of how the pulse shaper works. Let's go over it again. So input is this guy. Basically what it does, comes from, you have some input of electric field in time. Your first lens on the grating converts into electric field distribution in frequency. Your SLM adds or multiplies a phase as a function of nu, and that of course is spatial in SLM. The second lens does Fourier transform, and then you will get a E out of t, which is Fourier transform of the input field in frequency times a phase. So a phase is effectively imparted on it. So if the phase happens to be a linear spectral phase, which is coming from a linear tilt in a spectral phase profile, you can show that this amounts to adding a finite delay. Okay, so this basically, if you write down the expressions explicitly, by the way, these are different profiles that we can apply on SLM. The top two are kind of linear profiles. By the way, this is frequency. This direction is frequency. This for different pulses, we can kind of put them as lines here. So I can put, for example, one pulse here and the other pulse here. This is a sawtooth pattern, and the amplitude of the sawtooth pattern is A, which goes into this. But deep inside, what you cannot see is the phase here, and I can kind of make this phase go linear. In this case, it's going linear. Okay, there's the phase applied, and you can show that if I have an input field some f of t, what I'm getting out is actually f of t plus tau, which comes from this, and that is roughly the phase adder. Okay, now the thing that I want to highlight is that if you go through the math, you will see that there is one carrier frequency coming out. Now this carrier frequency is basically, this is as a function of frequency, right? Now there will be, if I'm applying a linear phase pattern, I can define some part of this frequency spectrum where, because it's linear, where my phase is 0, right? So the phase is 0. It's not changing. I'm not changing that. I'm applying phase elsewhere. Okay. If I do that, then you can show that that is my carrier frequency, which is where the phase is constant, and this is exactly similar to working in the so-called rotating frame, where you are now measuring coherences not with respect to omega 1, omega 0 difference, ground and excited state difference, but with respect to your carrier frequency, which is kind of very powerful now, because you don't need to worry about doing very short time delay oscillations. You can kind of scan the oscillations will become even more nice and easy to kind of probe, so on and so forth. And more importantly, if you apply a delay between the two pulses this way, simply by applying a phase pattern, what are you doing? It's like showing a pattern on a screen. Is exactly that. SLM is a little screen, and you are kind of showing a pattern. There are no moving parts in the setup. Since there are no moving parts in the setup, the interferometric stability is spectacularly high. Okay. So the critical part for you to go and think about, it may be confusing for now because I didn't explicitly do the math, is that how in a 4F system, if I apply a particular phase pattern on the SLM, how it's going to manifest in the output field. And the kind of summary lies in this particular box which I wrote. Okay, so I introduced two concepts at the same time. I introduced the concept of relay imaging and also added the complication of spectral content and temporal content to it. So you might find it a bit confusing for the moment, but I want you to go back and think over it and come back to me if you have questions. Okay, but the idea is you are using scalar diffraction theory, Fourier optics, to access the frequency space, right? And then applying a phase pattern there and see it manifest in time domain. It's kind of very beautiful demonstration of how spatial Fourier optics can enable you to structure electric field in time and spectral domains. Okay, so in fact, this pulse shaping can also be used to generate pulse replicas. I will not talk about this right now. So you can also generate strain of pulses. You send a single pulse and generate two pulses. Anyway, we can use this pulse shaping, like what is shown here, to generate the delay between the two pulses. Okay, so that's what we do. I'm going to show you the actual setup. It looks a bit complicated, but it's actually very elegant. You have from the NOPA things coming in, and this is your diffractive optical element which generate your four pulses. Okay, there is a mask. The mask is to ensure there are no spurious things. These lenses are part of relay imaging, carefully selected, extremely carefully selected and well placed. In fact, these on rails had to be put on rails carefully. So it goes onto this. This is a diffraction grating. It disperses light. This is a cylindrical lens. It goes and focuses on the SLM. And as you can see on the SLM, you have four lines, right? You have four lines. These are your four pulses. And if you add a finite linear phase between these two and scan that phase, it's equivalent to adding a delay between the two pulses. Okay. So basically this is your frequency. We usually take the center frequency as our carrier frequency, where the phase is going to remain constant throughout the pulses, and then we apply some kind of linear phase shift to the rest of the pulses. Okay, after it comes back, it travels through same path with slightly different tilt, so that we can pick it out. It goes then on to the experiment. It goes on to the experiment here. From the pulse shaper, it comes here. There is an optical density filter etched such that we can reduce the intensity of only the local oscillator pulse. It goes into a cryostat, and that's the configuration that is going into the cryostat, which is then picked up, and we send only here it shows everything goes in, it doesn't go. We kind of block. We have irises here to block off everything else apart from the signal, along with the local oscillator, goes into the spectrometer. Okay, that's the kind of, somebody asked, they wanted to see a 2D spectrometer in some class, and that's the 2D spectrometer design. Some images here. If I just take the boxcar geometry, these are the four. This is just putting a second harmonic crystal, and you'll generate all kinds of self and cross correlation between them. It kind of looks beautiful. This is how we calibrate. In fact, it's used to compress the pulses too. Your actual data looks something like this. This is as a function of wavelength. You have some interferogram, and you scan the delay between the first two pulses. In this case, there's a refacing spectrum, and then once you have this, the way we actually do it is, remember, this is all with respect to the carrier frequency. The oscillations are with respect to carrier frequency. So the way we do it is we Fourier transform this, inverse Fourier transform this axis to get a two-dimensional interferogram, do a 2D Fourier transform, and then appropriately shift with respect to the carrier frequency to get the 2D spectrum. Okay, it's kind of things in a nutshell. It's kind of it. If you have more questions on this, I'll be more than glad to answer. I can also share some resources on experimental setup. The important thing is how the pulse shaper works, and that's at the heart of this. Okay, this is, even though it's kind of, I kind of say it's kind of very nice and beautiful, blah blah blah. It is still a bit complex setup. You need to ensure you do relay imaging properly. You need to ensure you appropriately calibrate your SLM. Easier said than done. Remember, all these SLMs are calibrated by us in-house with self-written codes, which are easier, pretty complicated, and aligning this on a daily basis takes time. Okay, especially if you want to get good signals. Okay, so they are not, and also I cannot simply, for example, if I have suddenly a microscopic sample, let's say a 2D flake of TMDC, I cannot easily put that TMDC right in here or introduce an objective in order to do 2D spectroscopy on a relatively small sample. It's not easy. So in that sense, there are limitations to it, but the spectacular thing is the interferometric stability is extremely high. So you'll get signal to noise ratio, which is unprecedented almost. Also, you will be able to clearly separate out each of the diagrams, refacing, non-refacing, to quantum. You'll be able to separate them out. It's a relatively long measurement, simply if you want to scan all of this. But again, there are no moving parts, it's applying patterns, so it depends, limited by the, let's say, the refresh rate of your SLM, which is an important part. Having said that, there are a number of groups now exploring different kinds of implementations of 2D spectroscopy. This is not something which is widely used. We use it, not widely used. I would strongly recommend you to go and explore this amazing perspective by Fuller and Olivier on different kinds of spectroscopies, especially the upcoming spectroscopy, where the claim is that you can still do 2D spectroscopy in pump probe geometry. The simple thing comes from the fact that in pump probe, you can have the pump and the probe, you excite the system. What they do is they split the pump into two pulses, and we have just seen how pulse shaper, a simple pulse shaper, will enable you to do that, and then do the pump probe and do a scan between these two using the pulse shaper, and with that you may be able to access 2D spectroscopy. Okay, and there are several advanced methods, both experimental as well as theoretical methods, computational methods, to be able to separate out each of the phase diagrams. There is a group of Giulio Cerullo in Milan, where they developed a technique called twins, with which they will do the same thing as pulse shaping. There is Tobias Bixner in Germany, who does similar kind of work using pulse shaper. They also access higher order nonlinearities reasonably simply, reasonably easily. A similar kind of setup is also available in Indian Institute of Science in the group of Vivek Tiwari, where he does again in pump probe geometry. All this is also compatible with microscopy, which makes it more versatile to be used on different kinds of setups. Having said that, there is still an ambiguity given that there is a lot more overlapping contributions. Remember, when you do pump probe geometry or collinear geometry, you don't have access to a powerful thing called phase matching. Phase matching intrinsically allows you to overcome the barrier of need to kind of ensure that your excitation pathway is one way or the other. Okay, and that's a great thing about the boxcar geometry. It intrinsically allows you to separate them out. The other geometries, it's a bit more detailed, ongoing effort. The claim is that it can still separate, partially true, but there is still need to optimize it. I want to end with one more technique, a 2D spectroscopy technique, because here in this technique, we use 4 collinear pulses and go into the sample and still are able to explore and identify 2D nonlinear response, separate out refacing and non-refacing. And these are based on phase modulation method, originally developed, proposed by Andy Marcus group in Oregon. Later on, Carlos Silva's group, my postdoc mentor, sort of implemented this while I was there in Montreal and later Georgia Tech with him. This looks complicated. There are 2 Mach-Zehnder interferometers nested in a larger Mach-Zehnder interferometer, lot of pulses. But let's talk about this. What we do here is a 4 pulse experiment, or 4 are intense. Okay, unlike the other one where only 3 are intense, 4 are intense. So you come with 2 pulses, you generate your population. First pulse generate coherence, second pulse generate population. Your third pulse projects that population onto a coherence. This is what third order nonlinear response, right? Then what you do in this particular technique, you come with a 4th pulse which projects that coherence onto your population. Okay, and this population, what does it do? It will decay over a period of time on its lifetime by either emitting light, or if you are in a device, it will generate a photocurrent. You integrate all those photocurrent. The claim is, if I appropriately do some kind of phase modulation between the two pulses, I will be able to access the nonlinear response. How is that possible? So the way this is done is that you come with your NOPA output, you have a pulse shaper to compress the pulse in this case, you have a beam splitter, you split it into two parts. In one part, you go through again another beam splitter, you generate your first two pulses, they're generated here. You send them through two acousto-optic modulators. Okay, two acousto-optic modulators, and then you also delay one pulse with respect to the other and you combine them. Keep that in mind. We'll come back to that. There is some acousto-optic modulation in a Maxon interferometry and a time delay added to it. Okay, keep that in mind. Let's come back to it in a while. So let's go back and rewrite the fields now. A bit of theory now instead of going to experiment. Now we know very well, if I have two field interactions, so I generate those two pulses, the first two pulses, I kind of modulate the phase between them using acousto-optic modulators. I'll come back to that, what does it mean. So if I come with these two pulses, I will generate a population. The time evolution of the population, we know very well, can be written like this, where R2 is a second order impulse response function. Everybody knows this, right? Everybody knows this. Everybody knows also this, hopefully. Okay. Now if I write it out explicitly, and assuming a condition where there is a bit of phase difference between the two fields. If you look closely, there is a phase difference between these two fields. Now in that case, you will see this time evolution of my second order population has that phase difference between the two pulses encoded in it. You agree with me on that? The phase difference between the two, right? Okay, so there's a phase difference between the two pulses, and also you will see there is oscillations at the frequency of the energy difference, and also decay, coherence decay happening at the difference between at the pulse interpulse delay T21. Two important things. I'm looking at the population. The population evolution in this case, if I have, for example, a phase difference between the pulse, then you will have these two components. Agreed with it? Now what we do is go back to the setup. As I said, there are two acousto-optic modulators. What are these acousto-optic modulators doing? They are modulating the phase of the pulses independent of the time delays. So they're adding a phase which is time oscillating, like this, with capital omega j being the frequency of the oscillation. Usually acousto-optic modulators modulate at very high, we chose very high rep rate, about 40 megahertz or so. That is the frequency of the modulation of the phase of each of the modulator. But remember, we need the phase difference between the two pulses. We need the phase difference between the two pulses. So what we do is we slightly change the modulation frequency, slightly change, 40 megahertz, the other one is 40 point something megahertz, such that the frequency difference happens to be in the kilohertz range. Okay, so that's my phase which is added. So what I do now, like if I add my both the let's say the pulses now, add the both pulses, that's my phase added to my electric field, that's my phase difference, which will be time oscillating at the frequency of modulation difference between the two pulses. Capital sig omega 21 is differences in the modulation frequency between these two acousto-optic modulators, which happens to be about a few kilohertz. Okay, everybody fine with this? Kind of get it? Of course, I'm assuming that you already kind of know acousto-optic modulators. If not, go back and read a bit on acousto-optic modulators. Now, if I forget these two pulses, let's say we have only two pulses here, not four. So you go and excite the sample. This generates a population. We already know the population is oscillating. Sorry, it has a component of the phase modulation or the phase difference between the two pulses. Now, because of the phase modulation done by our Mach-Zehnder interferometer, this equation, this will be time oscillating. This will be time oscillating at the frequency of the difference between the two modulation frequencies of the acoustoptic modulator. Okay. So now I can use a technique called lock-in amplifier. Lock-in amplifier picks out signal like needle in a haystack. It's like this. It's like a tape your radio, right? So what you do in radio, you tune the frequency. What you have inside your radio is a phase lock loop, which by kind of locks onto the frequency of the signal. There's a local oscillator which locks on and extracts your signal. We can go on talking about lock-in amplifier, but the thing is, now I use my lock-in amplifier, give the input. So I take this, you excite the sample, it emits light, for example. Okay, I use a slow photodetector, collect all photoluminescence, okay, and then put it in a lock-in amplifier. I demodulate the signal exactly at the frequency of omega 2 1, the frequency difference between the two modulation frequencies. And it can be shown that my lock-ins outputs, my in-phase and quadrature components, can be written like this. Okay, very nice. I mean, basically you're extracting out the response function, impulse response function, second order, you're extracting out. This is kind of a bit not that useful. Now you expand this technique with 4 pulses. If you expand this technique with 4 pulses, it can be shown that you get 4 different contributions. These 4 different contributions are not that different from the different diagrams that we have already seen, the rephasing and the non-rephasing diagrams. The only thing is, now there are 4 pulses. Remember, there are 4 pulses. This 5, 4, 3 is the phase difference between the 4th and 3rd pulse. 5, 2, 1 is the phase difference between the 2nd and 1st pulse. And you will see that the rephasing and non-rephasing signal now are going to oscillate at specific frequency differences, okay, or frequency additions. Not going to do this. I mean, basically what you do is you take photoluminescence from the sample, connect it to your lock-in amplifier and demodulate the signal at the sum of the phase difference of the modulation and also difference of the phase difference modulation. Okay, complicated way of saying things, but basically what you're doing is you're generating a 3rd order coherence, projecting it onto your population, but then there is some intrinsic phase oscillation here which is preserved with the population that you are creating, and that you are able to demodulate out. Okay, so you're kind of projecting your 3rd order coherence onto your population which you're able to demodulate. Okay, it's kind of a complicated way of looking at it. If you're interested, it's a beautiful paper. This is almost like it's a read for a 1 month. You can kind of go over this paper. It's very dense paper, goes into this concept of phase modulation, which is a very powerful way, just completely different from all the other techniques. But then you can access the phase modulation. These are the signals that look like there are 2 delays. You can see everything is written in French because this is taken from PhD thesis of one of the students I was working with in Montreal. This is data, but that we can measure 2D response functions. For example, this is taken from a polytriaxylthiophene, a polymer commonly used in photovoltaic cell, taken at 5 Kelvin. One problem here is that you're measuring coherent nonlinear response, which is projected onto a population and letting the population evolve. So think of this, in the normal 4-way mixing kind of method, you're generating a 3rd order polarization and you're measuring that response immediately. Here what you're doing, you're generating that 3rd order polarization, projecting it on a population, letting it evolve, integrate it, and because you have kind of encoded the third order polarization with a certain frequency, very specific frequency, you're able to pull the needle out of the haystack with a lock-in amplifier. However, you're letting the population evolve. If the population evolves, it can also interact between each other incoherently, no coherence involved. So one of the bigger problems in this particular technique is that there is incoherent mixing, which appears like a coherent signal, but it is not. If you're interested, we have a couple of papers just talking about this. You can go and read about this here in the recent 2022 paper, which we tried to kind of show, especially in. So this one of the things is this technique. You could potentially use a solar cell, a working solar cell, and measure the coherent nonlinear response of a solar cell by measuring a photocurrent. Extremely powerful, right? We are talking about how measuring nonlinear response function at low densities, low excitation fluence is complicated. Here we can go at extremely low powers because solar cell works at solar excitation densities, so it's extremely useful. But the problem is we have seen using a gallium arsenide solar cell that incoherent mixing is present, and which will completely give a wrong signal. So that's the problem of this technique. But the amazing thing of this technique is a collinear geometry, 4 pulses coming together. So it projects onto a population and you can read out the response, and it's very nicely compatible with microscopy techniques if you're okay with aligning 2 Mach Zehnder interferometers nested in another big Mach Zehnder interferometer. Okay. All right. So too much of a detail. I kind of wanted to put out that technique there. Even if you don't get it, think of it that I can use acoustic modulators and lock-in amplifiers to extract nonlinear response functions. The important thing for you to understand is this link. If you can understand this link, then everything else becomes simpler. So the important thing for you, if you go back and try to understand what AOMs do, what this omega MT means, and what is this phase difference entails, and how we can extract that using lock-in amplifier. So this one slide, if you can go back and kind of meditate it over, kind of understand this, then you would understand the technique itself. Okay. All right. So I kind of covered the experimental part, starting from no pass, two different configurations of 2D spectroscopy, one using boxcar geometry where I emphasize the role of relay imaging and pulse shaping, the other component where I to kind of measure nonlinear response. Okay, with that we closing all the discussion about 2D spectroscopy. Tomorrow's class will take a sneak peek into quantum realm and see what happens if I treat light as quantum light, what kind of information or what kind of enhancements can I make to existing nonlinear spectroscopies, or can I see nonlinear spectroscopy in a completely new light? That is something that